Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture we have seen when can a simple field extension of a field which is algebraic is Galois. That is, if and only if the minimal polynomial of a generator splits into linear factors over L and simple linear factors. So let me record this in the form of theorem for the future use also. This is very important observation. So I would write it as a theorem. So let pi be a prime polynomial over a field, be a prime polynomial over K, and L equal to K x mod ideal generated by pi. Then we know this is nothing but it is K small x, where x is a image of the capital X, and this is a simple algebraic extension of K. This pi is nothing but the minimal polynomial of x. Further, kx k small x, which is L over K, is Galois extension if and only if pi splits into linear factors and all these x1 to xn are elements in L distinct, and this n has to be the degree of pi. Then only it can be Galois extension. Okay, so this means what? This I want to rewrite in terms of the group action. This means, or equivalently, the Galois group of Kx over K operates on the zero set of pi in L simple transitively. So these are the new words which we have to define for the group action. Simple means, first of all, transitive means there is only one orbit, and simple means it's a free action. That means there is no fix, there is no isotropy. So let us recall in general. So recall that. So in general, so X is a set, G is a group, and suppose G operates on X. Okay, then we say that G is transitive, or G operates transitively. G operates transitively on X if X is non-empty and exactly one orbit. That means x, whole x is orbit of some element x, for some x. Once it is orbit of one element, then it will be orbit of every element. So in other words, the quotient space. So quotient space x mod g will be singleton. So this also I should explain a little bit more, but I will explain it after the definition of simple. Simple means, so the transitive is defined. Now we say that G operates or G acts, G operates simply on X means if Gx equal to X for some G in G, X in X, then it should imply G is identity, E, the identity in G. So the set that G is operating in our case, that X is our zero set, VL of pi. This is x1 to xn. And then every time, first of all the elements are related to each other by some G because it's transitive, and then it's unique. So therefore, as sigma varies, so this is same as sigma of x as sigma varies in the Galois group, L over K. L is, remember, L is the simple extension here, Kx, and this x1 is x. So if I know x, I know the next one, I know the next one, and all of them I know a sigma, and then all are distinct. So therefore, the order of this cardinality of this set will be cardinality of the Galois group. So, and which is the degree. Therefore, that is Galois extension. So that is, remember, punch line to remember is a simple extension is Galois if the Galois group operates on the zero set of the minimal polynomial of that generator in a simple transitive way. Okay, this also gives us another definition, which is very important definition. Okay, now this is definition about the polynomial. A prime polynomial pi x, pi in kx is called a Galois resolvent. If kx modulo ideal generated by pi, which is a field, is a Galois extension of K. No, this is equivalent to saying that the Galois group of this operates simple transitively on pi. That means the zeros of pi are all here in this field L, and they are different, and they are as many as the degree of pi. So that polynomial is called a Galois resolvent. So Galois resolvents will give you Galois extensions. And for example, in a characteristic zero field, if you take an prime polynomial, that always have different zeros because there is no repetition. But this again I will repeat it. So we have lots of polynomials which has zero, which has simple zeros. So this is, let me write, this is equivalent to saying not this pi is the product of x1 minus x1, x minus xn, where with simple roots x1 to xn, simple roots, simple zeros of pi, and all of them are contained in k small x. So that is the Galois resonant. So now I want to ultimately we will prove that so this is our aim to prove. What is the next aim to prove? This is our next aim, to prove that every finite Galois extension L over K is simple. That is, L is of the form K x for some x. And then we will know how to test whether this is Galois or not, because we just have to test on that minimal polynomial of x whether it has a simple zeros and all zeros lies in L or not. So the checking becomes simpler. Whenever I have a group G operating on the set X, so first of all, to write neatly, I want to introduce a notation. Instead of writing such a long sentence, I will simply say X is a G set. That means X is some set, G is some group, and there is the operation of G on X. Then I will call X to be a G set. And we have seen our main example to study is whenever I have given a finite extension, finite field extension, then gal L over K, this operates on L, or in the newly introduced notation, L is a gal L over K set. And then we have seen in general, this is what we want to study, this action. So now just recall that whenever X is a G set, what all data we have attached to that. For any X in X, we have the orbit, they are all G multiples of X, and we have the stabilizers. This is a subgroup of G, subgroup, the one which don't move X. So these are all G in G such that Gx is X, and these are all G multiples of X. And we have also seen that the cardinality of the orbit equal to the index of the stabilizer. Index is by definition cardinality of the cosets of Gx in G, and we don't have to specify left or right because the number of left cosets equal to number of right cosets. So this is very important orbit stabilizer theorem. Okay, and remember also that this X is now on X, this G operation will induce a partition. Or an equivalence relation, if you like, or equivalence relation. Two elements of X, you call X and Y, two elements of X, they say they are related by the action of G. If Y equal to Gx for some X, Y equal to G of X, for some G. That means the equivalence class of X is nothing but the orbit of X. And then this will give you a partition of the set X, and therefore X you can write it as a disjoint union of the orbits, distinct orbits. So these orbits you know because of the equivalence relation, two orbits either they are equal or they are disjoint, and therefore here we are only taking those orbits which are distinct orbits. You don't repeat here. Another way to say that this orbit you take element, this union is running over the number of orbits, that is the quotient set, that is X mod G. This is the quotient set of X by this relation, this equivalence relation, we call it tilde G. So the elements are orbits, distinct orbits, Gx, distinct orbits. That is the thing. So then when you want to compute the cardinality of X is therefore summation of the cardinalities of the orbits, and this is running over only the quotient set, and these orbits you can also replace it by the indices of the isotropy. This is also same thing as summation G Gx, and only the elements X which is running in the set of orbits. So that is how the group operation. Now if one wants to separate out the orbits which are singleton and which are non-singleton, so but I don't need it now, but I definitely need the another invariant of the group action, that is called, so suppose X is a G set, then I want to write what is fixed elements of X under G. These are all elements of G, these are all elements of X in X, such that X is fixed under every element of G. Gx equal to X for every G in G. So in the notation wise, if you want, this is the intersection running over G in G, fix Gx. These are all elements of X which are fixed under this G, and intersection means so for all. So this is the fixed points of X under the G action on X. Okay, now first in our case, this is the first observation I want to now note is, so maybe I write on the next page. So I want to compute the fixed points of the Galois group action on the bigger field L. So let L over K be a finite Galois extension, and let us put G equal to gal L over K. Then K equal to, if I take the fixed points of L, G action on L, the fixed points are precisely the elements of K. Obviously, so let me write this as a theorem. This is a theorem because we want to use it again and again. So proof. So let us note down what is this fix. What is this fix GL? These are all elements of L. All those y in L such that sigma y equal to y for all sigma in G. That is the definition of the fix. So what are sigmas? Sigma is in G. Sigmas are K linear maps. So sigma fixes every element of K. So obviously K is contained in fix GL. This is obvious. Since if you want, since every sigma in G is K linear. Next thing, note that this fix GL, this is a subfield of L. That is also clear because all that we have to check that is if there are two elements, it is closed under addition, subtraction, scalar multiplication. Scalar multiplication you don't have to check, addition, subtraction and multiplication and the inverse. But that is clear, evident from the definition of the fixed field, because if y is fixed then y inverse is also fixed. You simply apply, take the inverses, and because sigmas are the K algebra homomorphism, they will also preserve the inverses and so on. So this is also clear that it is a subfield of L. Let us call this subfield to be M. And what is our problem? Our problem is to prove M equal to K. So we need to prove K equal to M. Alright, this inclusion is obvious, we have checked. Now I want to prove these are equal. So let us look at the Galois group of G was the Galois group of L over K. This is our G. And what is the relation between this Galois group and the Galois group of L over M? This is contained in M, L. Therefore, I can also consider the Galois group of L over this field M. So that is this. But you see, if somebody is M linear, then it is K linear also. So obviously this is contained here. But if somebody is K linear, that is also M linear, because we know all elements of these are already fixes M. So therefore it's equality here. So since every sigma in gal L over K is also M linear, because it fixes, because fix sigma L, this contains M, or fix. So it's clear, I don't write more. It is M linear because every element of Galois group fixes M, because that is the definition of the fix points of G action of L, G action on L. Therefore it is, this equality is clear. Now I want to apply Artin, Dedekind Artin, apply Dedekind Artin to this field extension L over M. Then what do I get? The cardinality of gal L over M is smaller or equal to degree L over M. But this cardinality is also same as, because their equality, that cardinality of gal L over K. But this again by Dedekind Artin to L over K, actually we know this is equality because we are assuming our extension is Galois extension. This is L over K because this is Galois. Therefore this equality. So this. But on the other hand, M is a field in between. So this is also same thing as L over M times M over K, because the tower of extension degrees are the product. So we have this equality is less equal to this, but it's already a factor here. So that implies this has to be 1. So that implies M over K has to be 1. It's one dimensional. M is one dimensional over K, but that means M equal to K. So what we have proved? We have proved that if you have a Galois extension and you take the fixed points of that, then you don't get a bigger field than the base field that we started with. This is very important. This is in fact one alternative definition of Galois extension. So then later on we will collect what are the equivalent conditions for a field extension to be Galois extension, and this will be one of them. And this also is one way to get rid of finite extensions, because we have said that a finite extension is Galois if some equality holds. But if your extension is not finite and you still want to define it as a Galois extension, then we have no numbers, no integers involved with that, but we have a fixed field, and the fixed field should be a ground field, and that could be one alternative definition. But we will have to prove the converse is also true. So this is what we will do it in a due course, and we will continue this. Next time I will prove that every Galois extension is simple. Therefore it will have primitive element and so on. So thank you. We will continue next time.